the first section we're going to be covering together is section 1.3, which is on relations and functions. We are going to go back and do section 1.2, which is on circles, a little bit later, but this topic is really crucial throughout the entire semester of pre-calculus and every semester of calculus you're going to take, so I wanted to go ahead and start with that. Okay, so a relation is just a set of ordered pairs. Okay, so an ordered pair, well, it's a pair, so there are going to be two things, and there's an order. So there's a first thing, and there's a second thing. Okay, these pairs can be of just about anything. For example, if I look at the roster for this class, I can view that as a relation, because for each one of you, I have a first name and a last name. So I can think of each of you as an ordered pair of names. And it is an ordered pair because there is a first name and a last name as well. So that's an example of a relation. And as you'll see, we don't just sort of mix and match things at random. It's called a relation because we usually take these ordered pairs when there's some connection between them. This first name goes with that last name because they belong to the same person. Now, this is a math class, so most of the relations that we're going to be working with, we're going to have ordered pairs of numbers. And generally when we have that, we'll say that the first term is the x value and the second term is the y value. So we'll have ordered pairs of numbers, x and y. So a relation is just a set of ordered pairs. Now these braces are set notation. Okay. So for example, 1, 2, and 0, negative 5, that's a lovely relation. That's a set of ordered pairs. This happens to just have two ordered pairs in it, so it has a finite number of elements. This is one way that I can give a relation. It tends to work well if I have a small number of elements. Here I just have two of them, so it's possible for me to list them all. Very often, though, we're going to be working with relations and functions, and I haven't defined a function yet. I will. It's a special type of a relation. But we're often going to be working with relations and functions where there are infinitely many points. And when that's the case, most of the time we're going to be describing those either as an equation, something like y equals x squared. Now that would tell me that my relation is the set of all ordered pairs, x and y, where the y value happens to be the x value squared. Now there are infinitely many of them, so I can't write them all down, but this relation would include, just as a couple of examples, it would include the point 2, 4. X is the first value, that's 2. My y value of 4 is 2 squared. 3, 9 would also be part of this relation, so would 5, 25. But the relation is much more than just these 3 points, and that's why we give the equation. It tells me what the relationship between x and y is for an ordered pair to be considered part of that relation. So very often we'll be working with equations. Another way that we can easily work with infinitely many points, that also works for finitely many points, is to draw a graph. Okay. Now, if I take a look at this relation, I could certainly say, hey, an ordered pair of values right here, every ordered pair corresponds to a point in the xy plane. So the horizontal axis is my x-axis, the vertical axis is my y-axis. If I wanted to plot the point 1, 2, starting at the origin, I'd come over 1, up 2, and there's my point 1, 2. If I wanted to plot 0, negative 5, starting at the origin, I don't go left or right because my x value is 0. I would count down 1, 2, 3, 4, 5. So here, this is the graph of this relation, of these two ordered points. So I can certainly graph a finite number of points, and each point corresponds to an ordered pair. But what's nice about graphing is that I can also graph infinitely many points. There's no way I could write down the coordinates of infinitely many points. But while y equals x squared has infinitely many points that are solutions to it, I can graph them all. I just did. Okay. Anytime I draw something like this, I've just drawn infinitely many points. There's a point here, that would be the point 0, 0. 2, 4 would be somewhere on here. Right around there, we've got the point 2, 4. All of these points are on there, but notice if this is 0, 0 and this is 2, 4, in between here there are infinitely many different points because there are infinitely many x values between 0 and 2. So anytime I draw any line or curve like that, I've drawn infinitely many points. So a lot of times the relations and the functions that we're working with will have infinitely many points, and so we'll be working with equations and with graphs so that we can work with infinitely many points at a time. And one of the big things that we'll be looking at is the connection between the equation and the graph. Basically, a point here on this graph is going to be a point is going to be on the graph if its coordinates, its x and y values, make this equation true. Okay. Now, a function is a relation that follows a particular rule. So a function is a relation, so it's a set of ordered pairs, such that each input and the input is just going to be our first term. It's an ordered pair, so there's a first term and a second term. I'm going to call the first term the input, and the first term is usually going to be called x. Every once in a while, we might use a different letter. We might be talking about things that are functions of time, so we might have t values instead of x values. But whatever the first term is, we're going to call that the input, and it's going to have a unique output. And the output is just the second term, and that's usually going to be denoted as the y value. So each input is going to have a unique output associated with it. So in that sense, I can sort of think of a function as a machine where I'm going to plug in something. I'm going to plug in the input. The function's going to do something to it, and it's going to spit out the output, the result. But this rule says there's going to be a unique output. If I know what I've plugged in, that tells me for sure what this machine ought to plug out. I don't have multiple options. I like to tell a story when I talk about functions. When I was in grad school, my office was up on the 10th floor of the math building, and the soda machine was down in the basement. So I would travel all the way down to the basement when I needed a break from my studies, and I would put my coins into the soda machine, and I would always hit the Dr. Pepper button. And I was sometimes greatly disappointed because sometimes I would get what I wanted. I would get a Dr. Pepper. And other times, do you know what I got? I got an orange soda. I don't like orange soda. And in case you haven't noticed, I'm still bitter. Okay? Now, the problem is that soda machine was not functioning. It wasn't working properly. It wasn't working like a function. If the input was me hitting the Dr. Pepper button, there was supposed to be one and only one possible output, and it was supposed to be a Dr. Pepper. And the problem is, there were two different outcomes. Sometimes it was a Dr. Pepper, sometimes it was an orange soda. Because I got the Dr. Pepper some of the time, I would forget about the times that I got the orange soda. I would go back to that stupid machine and I would hit the Dr. Pepper button, and then I'd be greatly disappointed because I'd have my orange soda. Granted, I should have learned my lesson sooner than I did. But anyway, that happened. But with a soda machine, that's supposed to behave like a function. If you hit a Coke button, you should get a Coke. If you hit a Dr. Pepper button, you should get a Dr. Pepper. If you know what button you pushed, if you know what the input was, that should uniquely determine what the output is. I want to just point out that this is a little bit of a double standard. Okay? Have you ever seen a soda machine with two Coke buttons? I have. And if I hit the first Coke button, I should get out a Coke. If I hit the second Coke button, now that's a different input because it's a different button, I should still get out a Coke. Perfectly acceptable for two different inputs. Think of that as two different buttons that you can push to lead to the same output. Now, I am told that there are soda machines out there with two Dr. Pepper buttons. I have never seen such a magical object. I would love to see a soda machine with two Dr. Pepper buttons. I've never come across one in my life. I hope to someday find a soda machine with two Dr. Pepper buttons. But that's the rule for a function. Okay? If you know what your input is, it should determine a unique output. But it's perfectly acceptable for there to be multiple inputs that give you the same output, just like it's perfectly fine to have multiple buttons on a soda machine corresponding to the same soda. Okay, what we're going to do next is start taking a look at some various ways that functions and relations can be defined, because they can be described a bunch of different ways. Like I said, most of the time this semester we're going to be working with equations and graphs, but there are lots of other options as well. So we're just going to sort of work through those. And starting with the next video, I've got this worksheet that was posted on Canvas with these videos that just lists the problems that we're going to be working through. If you want to have this with you, you certainly can. You should be taking notes because obviously we weren't using it, and I've been talking for a while. So you should be taking notes so you've got your definitions of function and relation. But as we work through this worksheet, if you don't want to have to copy down the problems, I will write them on the board so you don't need to have this. But if you want to have this so that you're not spending a lot of time just copying down the problems, you'll want to have this handy for the next video.